Hello everyone, my name is Joe D'Angelo from Materials Today, and I'd like to welcome you to our 7th Materials Today webinar of 2016 entitled Chemistry and the TEM, New Horizons for Catalyst Research, which will be presented by Dr. George W. Graham, who's an adjunct professor at the University of Michigan and a project scientist in the Department of Chemical Engineering and Materials Science at the University of California, Irvine. He'll be joined by Shuyi Zhang from the University of Michigan and Ben Jacobs from Protochips. And this webinar is sponsored by Protochips. As you know, Materials Today strives to bring you educational presentations on some of the most exciting topics in materials science as part of our webinar series. So please do visit our webinar page regularly to find out more about upcoming events and recordings of past webinars. So back to today, it's my pleasure to introduce and welcome today's speakers. So Dr. Graham has been active in the study of catalyst materials for over 3 decades. He spent more than 20 years in the scientific research laboratory at Ford Motor Company before joining the Materials Science and Engineering Department at the University of Michigan as an adjunct professor. And as I mentioned, he's also a project scientist in the Department of Chemical Engineering and Materials Science at the University of California, Irvine. Shuyi Zhang is from the University of Michigan, and her research on structure-property relationships of nanomaterials have resulted in a number of publications in top scientific journals. And Dr. Ben Jacobs is the product manager at Protochips, where he oversees all product lines. He's worked for Protochips since 2010 as an applications scientist and then the applications manager before becoming the product manager. He obtained his PhD in electrical engineering from Michigan State University and studied the structural and electronic properties of semiconducting nanowires, including gallium nitride and carbon nanotubes. His postdoctoral work was done at Sandia National Labs in Livermore, California, where he worked with porous metals for hydrogen storage applications. So after that introduction, let me remind the audience of the structure of today's event. The presentation will begin shortly, and following the presentations, there'll be 2 presentations. Following the presentations, we'll have a question and answer session. I'd encourage you to please input questions as and when you think of them during the presentations by using the Ask button on your screen. Questions will be addressed in the Q&A session at the end. The more questions asked, the better the session will be, so please don't hesitate. So also, if you're using Twitter, please use the hashtag MTWebinar when tweeting about the event or to reach out to the Materials Today team directly. So let's begin. I'd now like to hand over to George Graham to begin his presentation.
Good afternoon. My name is George Graham. For the next half hour or so, my colleague Shuyi Zhang and I will discuss some of the work done recently at University of Michigan using in situ microscopy and spectroscopy to study catalytic material. Our presentation consists of 2 parts. I will begin with a few general remarks about catalysis research, after which Shuyi will introduce scanning transmission electron microscopy, or STEM, and develop the case for why it is so interesting and useful to those engaged in catalysis research. We will then launch into a description of our application of in situ STEM to one of the most studied phenomena in catalysis research, the strong metal support interaction, or SMSI. Those interested in more details about this work can find them in our paper in Now Letters. So, what is catalysis research about? I should first take a step back in order to place catalysis in the larger context of chemistry, which is essentially the science of making things. For example, how 2 reactants, A and B, combine to make distinct products, C and D. Catalysis is about altering, usually increasing, the rate of such a chemical reaction, or altering the selectivity with respect to product distribution. Since I come from automotive industry, I like to use the exhaust gas catalyst, or catalytic converter, as an example. Most everyone knows that one of these devices is installed in the exhaust system upstream from the muffler in their car. The function of the catalytic converter is to promote the reaction of unburned hydrocarbons, nitrogen oxides, and carbon monoxide present in the exhaust gas that exits the engine into water, dinitrogen, and carbon dioxide before the gas is released into the atmosphere. Typically, the catalytic converter is comparable in volume to the engine's displacement, a few liters, and since the engine operates at hundreds to thousands of RPMs, the residence time of gas in the converter is on the order of tens of milliseconds. A thermal reactor would not be capable of handling such a large gas flow, and thus catalytic action is required in order to achieve a sufficient reaction rate. It is important that certain undesirable products, like ammonia, not be produced, however. Thus, the catalytic converter is designed to be both active and selective in the reactions it promotes. The appearance of the catalytic converter is deceptively simple, a ceramic monolith filled with many straight-through channels that offer little resistance to exhaust gas flow. But there is another level of structure, easily seen with a magnifying glass, consisting of the so-called washcoat, which contains all of the important ingredients of the catalyst. These electron microprobe images of a small cross-section of the washcoat layer provide some idea of the real complexity embodied within the catalytic converter. A typical formulation contains more than half a dozen different oxides, each of which has been carefully chosen to perform a specific function. The most important component, however, is the precious metal, usually a mixture of platinum, palladium, and rhodium. These metals, in the form of highly dispersed nanoparticles, provide the active surface sites where the chemical reactions actually occur through a sequence of elementary steps, including adsorption of molecules, breaking and reforming of intramolecular chemical bonds, and desorption back into the gas phase. Catalysis research involves the investigation of such reaction processes at the molecular level, with the ultimate goal of understanding the reaction mechanisms in great detail at the microscopic scale. It is generally accepted that detailed knowledge about the structure of the catalyst under reaction conditions is critical to achieving this understanding. At this point, I'll turn the presentation over to Shu-Yi, who will introduce the STEM and explain why ambient pressure STEM is so useful for catalysis research. Here's Shu-Yi.
Hello, everyone. Now let's look at the motivation and background of ambient pressure STEM. Scanning transmission electron microscopy is a combination of SEM and TEM. A highly focused electron probe is raster scanned across the material, and images are formed by transmitted electrons. It's a newer technique comparing to conventional TEM, and it has several advantages. First, it enables spatially resolved spectroscopy information. For example, when the probe is raster scanned across the sample point by point, then we can know the chemical information point by point. By installing different detectors, different signals can be collected simultaneously. For example, if we collect electrons that are scattered at high angle with respect to the optical axis, then we'll form high-angle annular dark-field image. It's similar to Rutherford scattering, so it is a Z-contrast image. The higher the atomic number, the brighter it will appear in the image. If we collect electrons that are scattered at relatively low angle with respect to the optical axis, then we'll have bright field image. It's a phase contrast image, similar to HRTM. And those images are formed by elastic scattered electrons. If we collect electrons that have transferred sufficient amount of energy to knock out core shell electrons of the material, then we'll form electron energy loss spectroscopy. Below is an images showing palladium nanoparticles supported on TiO2. The left one is a high-def image, and the right one is a bright-field image. bright-field image. Is a bright field image. And those images are formed by elastic scattered electrons. If we collect electrons that have transferred sufficient amount of energy to knock out core shell electrons of the material, then we'll form electron energy loss spectroscopy. Below is an images showing palladium nanoparticles supported on TiO2. The left one is a high-def image, and the right one is a bright-field image. As most of the high-resolution technique, it requires to work under a high vacuum environment. But why we bother to introduce gas into the microscope? The reason is because most catalysis work under gaseous or liquid environment at elevated temperature, and their structure and composition are likely to change in the reactive environment. And those changes usually have profound influence on their property and stability. For example, some of the nanoparticles will involve a systematic shape change as it explodes to a certain gas, for example, CO or water vapor. They will change from a round shape to a faceted shape. Therefore, understanding the structure of catalysts and the realistic conditions with atomic scale precision is crucial to design better materials for challenging transformation. There are two approaches to achieve in situ electron microscopy. First is environmental TEM. And this is a picture showing FEI, Titan ETEM. Here we can see the gas is primarily confined in the sample area, and they use additional pumping system to maintain a pressure differential between the gas to the sample area. A newly developed technique is MEMS-based gas cell, and this is the technique we are using right now. As shown in the picture, the primary change is only made on the TEM holder. The gas and sample are confined by two pieces of E-chips and sealed by an O-ring. Here is a comparison between ETEM and gas cell. The primary disadvantage of ETEM is the pressure. It can only go up to 1% of 1 atmosphere pressure. But the difficulty has been easily overcome by gas cell. We can easily go up to atmospheric pressure. The second disadvantage is the cost. Usually, aberration corrected TEM costs a few $1 million. And ETEM requires additional modification of the column and pumping system. So it's going to be more expensive than regular TEM. But the price of the gas cell is much, much lower, and also it's flexible. When one microscope is done, you can easily transfer it to another microscope. The advantage of ETEM is the imaging and spectroscopy capabilities are essentially pretty much similar to a conventional TEM. But because the gas cell has a membrane, the contrast, resolution, and spectroscopy capabilities will inherently be compromised. The electron length in the gas containing area for ETEM is on the order of millimeter. So gas ionization is another issue. But gas in gas cell is only confined in a 5 micron region. So usually most of the electrons are not scattered by the gas at all. For the ETEM, most of the holders are double tilt, so you can orient your sample at your preferred orientation. But for gas cell, the holders are usually single tilt, and the sample geometry are constrained. There is also a potential danger of membrane rupture. So now let's use a material example to see the capability of the gas cell. Strong metal support interaction will be talked about by George.
So the term SMSI was first used by Sam Tauster and his colleagues at Exxon Research Labs to describe the suppression of hydrogen and carbon monoxide chemisorption by metals supported on titania following reduction at high temperature. Many such examples involving reducible oxide supports were identified and studied subsequently extensively over the years. Both electronic and geometric factors were considered as possible explanations for the effect, but eventually it became clear that a thin layer of partially reduced oxide was migrating onto the metal particles, blocking access to gas. For example, a number of elegant scanning tunneling microscopy studies have been performed on model catalysts consisting of metal nanoparticles deposited onto single crystal oxide substrates and vice versa that confirm this behavior upon heating in vacuum and also provide structural information about SMSI-like analogs. Shown here are some representative results which demonstrate that migration has occurred. This is shown in panel A by low-energy ion scattering. Also, how the model catalyst looks at various magnifications, shown in panels B through E, and finally an IV curve that provides some information about the electronic transport across the oxide layer. In addition, many ex situ TEM studies have generated images showing an amorphous layer coating titanium-supported metal nanoparticles after reduction treatments. Note that these images don't appear to have much in common with the STM images. Furthermore, they don't provide clues about the effect of reduction conditions on SMSI, which are known to be important. Thus, we decided to look at what's actually happening during reduction treatments. Xu-Yi will now tell you more about what we learned.
This is a palladium nanoparticle supported on TiO2, and the condition that we used to acquire this image was 250 C 5% hydrogen balanced with argon with 1 atmosphere pressure. And here we can see there is a very thin amorphous layer migrating onto the particle. And if we increase the temperature to 500 C, we can start to see the formation of a crystalline bilayer on the surface of the metal particle. If we compare with the high-def image, which is a Z-contrast image as we have stated before, the crystalline bilayer is almost invisible in the high-def image, indicating it has a much lower atomic number comparing to the palladium nanoparticle underneath. If we change the atmosphere to oxygen 150, which is comparable to the oxygen particle pressure in air, we can start to see the breaking up of the over layer. And if we wait longer time, it gradually dissociates. If we increase the temperature to 500 C, we can see it entirely dissociates. But if we change the gas to 5% hydrogen balanced with argon again, the crystalline bilayer reappears. So this process is reversible. And let's review it again. So 200 C forming gas amorphous layer, and 500 C crystalline bilayer. And here we can see the crystalline bilayer is epitaxial to palladium 111 surface. And if we switch to air, it dissociates. If we go back to forming gas again, the crystalline bilayer reappears. Now we want to correlate the structure with the chemisorption capability. The amorphous layer corresponds to the state produced by low temperature reduction, where we can see most of the metal sites are still active in absorbing gas molecules, indicating the amorphous layer is gas permeable, while the crystalline bilayer corresponds to the state produced by high temperature reduction, where we can see almost all the metal particles are that they cannot they cannot absorb gas molecules anymore, indicating the crystalline bilayer is very effective in blocking the access of gas molecules. I also did an EOS line scan from in the sample at 500 C under forming gas. Here we can see the valence of titanium is 4+ on the support and changed to 3+ on the metal particle, indicating the support has now been reduced by forming gas, but the particle is covered by a very thin layer of reduced titanium. And this is the reaction equation. TiO2 with hydrogen and palladium result in the formation of TiOX on top of palladium and also water vapor. If we assume that water vapor is in equilibrium with hydrogen and oxygen, then it's equivalent to the second reaction equation. Here we can see the equilibrium of this reaction is only depend on the oxygen partial pressure and temperature. So my collaborator from Stanford calculate free energy for different TiOX phase on palladium 111 or palladium 100 surface as a function of oxygen chemical potential. Because we are only focusing on 111 surface of palladium, and it's confirmed that the surface layer is K-phase with hexagonal geometry, so here we only need to focus on the solid black and solid red curve. We can see there is an intersection between the two curves at oxygen chemical potential equals to minus 3.7 eV. So this indicates when the oxygen chemical potential is below minus 3.7 eV, the crystalline bilayer is the most stable phase. Well, we can see another intersection of the solid black curve, black line with 0. So between minus 3.7 eV to minus 2.8 eV, the crystalline monolayer is the most stable phase. Well, if the oxygen partial potential is higher than minus 2.8 eV, the null layer will form on the surface of the metal particle. After he finished his calculation, he asked me to confirm it experimentally because the gas cell we received was not capable of mixing gas, so we designed a special technique to mix a little bit hydrogen and a little bit oxygen in the gas cell, and when the system reaches equilibrium, corresponding oxygen chemical potential can be calculated. In the case of 5% hydrogen balanced with argon, it corresponds to an oxygen chemical potential less than minus 3.7 eV, and we did see the formation of the crystalline bilayer. Well, if I mix 4.9% of hydrogen with 2% of oxygen in the gas cell, it corresponds to oxygen chemical potential equals to minus 2.8 eV, and we did see the formation of monolayer. If I mix 4.7% of hydrogen with 5.7% of oxygen, then it corresponds to an oxygen potential equals to minus 0.8 eV, and we didn't see any layer formation. So here the theory and experiment agree with each other very well. And next I'm gonna to show the shape change induced by the formation of the overlayer. This image was taken under 4.9% of oxygen balanced with 2% of 4.9% of hydrogen balanced with 2% of oxygen. An image was taken at 400 C. After 25 minutes, at this temperature, we can start to see the formation of the overlayer, accompanied by the shape change. And if we wait for longer time, we can even see the aspect ratio change of the particle. It becomes taller. And if we increase to 500 C, we can start to see the steps formation on the side of the particle, indicating the migration of surface atoms. And then it reheals. And this is the final state of the particle. If we compare the initial state with the final state, we can clearly see the shape change happened during this process, and we want to have a more quantitative understanding of the shape change from a round particle to a faceted particle. So I labeled each facet. Here the top surface is 100 facet. The bigger one on both sides highlighted in yellow are 111 facet, and the two smaller ones highlighted in purple is 110 facet. If we compare the initial stage with the final stage, we can clearly see the disappearance of 110 facet, the expansion of 111, and shrinking of 100. And here we use Wolf construction. Wolf construction can correlate the surface energy ratio between two facets with the area ratio of two facets. The lower the surface energy, the bigger the area it will appear in the particle. And also, it is proportional to NT over NP. NT is the number of atomic columns from 100 surface to the diameter, and NP is the number of atomic rows in the diameter. So here we can see surface energy of 100 over 111 increase from 1.08 to 1.27. So this indicates that the surface energy of 111 has relatively lowered. It becomes energetically more stable than 100. So what is the reason? First, the adhesion energy between palladium and the TiOX overlayer is negative, so the formation of the overlayer results in the reduction of the overall surface energy. And for palladium, 111 has the lowest surface energy, followed by 100 and 110. If every facet is reduced by the same amount of surface energy, the one with the lowest surface energy initially will become even more favorable. For example, if we have 4 and 2 and both are subtracted by 1, then the ratio will increase from 2 to 3. In a similar way, the reduced surface energy the reduced surface energy results in the expansion of 111 plane, shrinking of 100 plane, and internally disappearance of 110 and other high index facets. We also did control experiment on platinum TiO2. The series says the overlayer will also be energetically favorable, and we did see the formation of the crystalline double layer at exactly the same condition. But gold TiO2 is another story. Through the calculation says that the formation of the overlayer will not be energetically favorable, and as a result, we didn't see any layer formation on the gold particle under the same atmospheric condition. Here is the summary of this project. We provided atomic scale detail of the dynamic process of SMSI state of palladium TiO2 system through ambient pressure, TEM, and DFT calculation. We found that amorphous TiOX layer is initially formed at low temperature in reducing atmosphere, followed by crystallization into an ordered epitaxial layer on palladium 111 surface at 500 C. The amorphous layer is gas permeable, while the crystalline bilayer is very effective in blocking access of gas molecules to the underlying metal surface. The reduced oxide is 1 or 2 atomic layers thick, depending on the atmosphere. Crystallization of the over layer is accompanied by a reconstruction of the palladium nanoparticle as a result of surface energy minimization. So this is a collaborative work through Michigan, Stanford, and UCI. I and my lab mates Shengdai Mingjie and Georgia from Michigan. Willis and Mateo did a catalyst synthesis, and they are from Stanford. Philip and Frank provide the expertise in DFT calculation. And Xiaojing Pan was used to be a faculty member in Michigan, and recently he moved to UCI. Finally, we would like to thank for all the help from the folks from Protochips and Masaka Kawasaki from GUL. All the experimental work are done in Michigan Center for Material Characterization with a lot of help from Haiping Sun and Kai Sun. We would like to thank for the generous funding from NSF.
Okay, thank you, Shuyi. Finally, I'd like to make just a few comments about what I see as the near-term future of ambient pressure STEM for catalyst research. First, I think there are many examples, like SMSI, where researchers are just curious to see what is really happening to a catalyst under reaction conditions. We've looked at more than a dozen systems over the past 2 years, and we have often been surprised by the results. I also expect there will be interest in looking at a number of generic problems like catalyst restructuring, nanoparticle coarsening, support sintering, chemical poisoning, and so on. Many of these areas have already been studied by TEM, but I suspect there will be interest in repeating some of these studies at higher pressure. A nice summary of this work recently appeared in Chemical Reviews, and I particularly like the approach described by one of the authors, Peter Crozier, who talks about following the full life cycle of a catalyst from synthesis through activation, deactivation, possibly reactivation, and finally end of life. Ambient pressure STEM should be even more applicable than TEM for this sort of work. And then for those who are in industry, I think there will continue to be a great deal of interest in better understanding catalyst durability, which again can benefit from microscopic examination of catalysts under even harsher conditions. That concludes our portion of the webinar, so I'll turn it over to Ben Jacobs from Protochips.
Okay, thanks, Dr. Graham. Hello, my name is Ben Jacobs, and I'm the product manager of Atmosphere here at Protochips. We just heard a great example of how our system can be used for top-notch research, and I really want to commend Dr. Graham and Shu Yi on their excellent work using Atmosphere. Now that we've heard an overview of what Atmosphere can do, I'd like to go in a little more detail about how Atmosphere works. But first, I want to give a brief description of the other products we offer here at Protochips. For the past decade, we've focused on developing in-situ solutions that transform one of the most widely used tools in nanotechnology, the electron microscope, from a camera into a complete nanoscale laboratory. As you can see, the gas cell is only one of the products we offer. Atmosphere is accompanied by Fusion and Poseidon Select. Fusion heats samples up to 1,200 degrees Celsius and can apply and measure picoamp level electrical signals and simultaneously heat and apply an electrical bias. The system is perfect for studying the electrical and thermal response of materials for research in the fields of sintering, phase changes, solid-state battery materials, and semiconductor devices. Our Poseidon Select system is used to image samples in their native hydrated environment. Poseidon is useful for studying biological and wet samples such as paints, inks, and gels. Electrochemistry can be performed for in-situ battery, fuel cell, and corrosion applications. We've also recently added heating capability for imaging samples in liquid up to 100 degrees Celsius. Lastly, we've got atmosphere, which we've already heard a little bit about. Let's go into more detail about atmosphere and why it's been established as the industry leader for in-situ gas cell microscopy. For those of you not familiar with in-situ TEM gas cells, I wanted to start with a brief description of what makes atmosphere unique. For starters, we've already seen an example of how atmosphere enables atomic resolution imaging at pressures up to 1 atmosphere and temperatures up to 1,000 degrees Celsius. It's fully compatible with EDS and EELS, which allows elemental analysis throughout the entire in-situ experiment. Perhaps most importantly, the system is safe. We are the only in-situ system manufacturer that works hand-in-hand with FEI and Joel to ensure our products meet their rigorous safety standards. Because we work so closely with the TEM manufacturers, you can be assured that our systems will not compromise TEM safety. So, how does atmosphere actually work? Atmosphere is a complete system that integrates seamlessly into the TEM. All components shown here work together to precisely control the gas environment inside the cell. We'll be going over each of these components one by one, but I want to start with the heart of the system, the E-chips. Protochips uses MEMS devices, which we call E-chips, to enclose the sample in a well-controlled gas environment and apply precise heating. At the center of the thermal E-chip device is a proprietary silicon carbide membrane heater, which is shown here. Now let's take a closer look at the closed cell itself. This is a cross-section of the gas cell. To heat the sample, an electrical current is passed through the silicon carbide membrane, shown in red here, and its temperature is proportional to the level of current. The carbide film is thermally uniform and stable with low drift and capable of heating to very high temperatures for many hours at a time. Most importantly, this membrane is chemically inert, so it doesn't interfere with your reactions like metal heaters can. Atop the silicon carbide film is a thin layer of silicon nitride, which is also thermally robust, chemically inert, and electron transparent in order to contain the gas without affecting TEM resolution. A second E-chip with only a silicon nitride membrane creates the gas cell. Different gas types and different pressures can affect the temperature of the cell, so we created a closed-loop temperature control system which automatically monitors and adjusts the temperatures regardless of the gas environment. To guarantee each chip is perfect for your experiment, we inspect and measure every E-chip with a commercial thermal camera to make sure the temperatures are accurate and precise time after time. A unique calibration file is created for every E-chip device, which is used by our software. This ensures everything works seamlessly so you can focus on your experiment. So now I'd like to move to the next part of atmosphere. As we said, E-chips are only part of the system, so next we'll focus on the holder itself, the component that holds and seals the E-chips and interfaces with the microscope. The holder contains 2 E-chips, the sample, and allows gas flow to form the sealed experiment cell within the TEM. Central to our holder design is a single O-ring gasket that aligns the E-chips and forms the hermetic seal required for TEM operation once the lid is screwed to the tip. The gasket design is unique to atmosphere and the key to making it the easiest to use system on the market. Now, you're probably wondering how we actually get gas into the TEM, and that's where the gas manifold comes in. This component of atmosphere is quite large, and that's because it houses all of the manifold lines, valves, and electronics that let atmosphere run autonomously in the background, so you can focus on your experiment. But how does atmosphere actually deliver gas to the cell? To describe this, I'm showing a schematic of the gas manifold to give you a sense of how our gas handling works. On the left-hand side are the gas inputs, which are color-coded to easily identify what gases are where. Atmosphere typically uses two experiment gases, such as a reduction gas and an oxidation gas. The third gas is for system purge, typically argon or nitrogen, which is used to clean residual experiment gases from the manifold. To get gas to the sample, first you tell the system what gas and pressure you want, and second, the gas is pulled into one of the experiment tanks shown on the right, and third, it's delivered to the cell inside the TEM holder in the middle of the screen. This whole process takes no more than about a minute. It's really that easy. This method of gas handling is reliable, repeatable, and safe. The last key feature of Atmosphere is the software that automates the gas handling, e-chip heating, data logging, and safety features. Just as with every other component of Atmosphere, the software has been designed to make in-situ experiments easier. We call it Clarity, since its ease of use helps you get better actionable data faster and delivers intuitive control to our unique system design. Clarity is centered around a simple workflow that guides you from the start of the experiment to the finish. It produces real-time readouts of the state of the gas manifold, including the pressure and holder temperature, and automatically records all system parameters throughout the experiment. With a click of a button, you can pump and purge, bake out the entire system, change pressures and gases, change from static to flow mode, and change temperatures. In the top left corner of the screen, you'll see the gas handling system, which we just described in some detail, and how it integrates with the rest of the software controls. Clarity has redundant safety features built into the system, such as automatic valve closure in the case of an unexpected leak, and is constantly checking and maintaining gas pressures. Again, we work with the major microscope manufacturers to make sure Atmosphere interfaces perfectly with the TEM, so you have peace of mind needed to focus on your experiment. The last key feature of the software control is a new software accessory we call Image Sync. Now, I'm really excited about this, and I think you will be too. Image Sync lets you synchronize any TEM signal, whether it's images, EDS data, diffraction, video, and so on, with in-situ data from Atmosphere. You don't have to keep track of timestamps or keep stringent notes anymore because Image Sync does it for you. But instead of just describing Image Sync, I'll play a video of it and we'll explain what's going on. On the left-hand side is a live view of a dark field STEM image showing nanoparticles inside the gas cell filled with forming gas. On the right-hand side, windows taken from the Clarity software are arranged in a custom configuration. Image Sync takes the live image or video feed from the TEM and data from the Clarity software to create a live view of the information most important to you. Changes in the sample are captured and synced with changes in the temperature and pressure, all in real time. So that's how Clarity and Image Sync work, but there are a few other components that complete the Atmosphere system that I want to discuss. A scroll pump is included with the system that pulls vacuum on the gas manifold, and there's also an optional leak check station which is used to ensure proper sealing of the holder and e-chips. So all these components work together seamlessly to deliver gas and control the environment inside the cell. And that's really how our system works in a nutshell. So if there's one thing that we want you to take away today, it's this. We don't view Atmosphere as just a new tool for the TEM. We view it as opening up a new frontier in the field of in situ microscopy. When you think about it, it doesn't make any sense that scientists must image their samples in high vacuum. There's really no need for it. With atmosphere, we're finally extending the capabilities of the TEM to transcend the limitation of the column vacuum. We heard from Dr. Graham and Shui about how the gas cell has had a huge impact on the field of catalysis, and we have similar stories from customers around the world. So if you'd like to know more about how to get an atmosphere system installed in your lab, you can reach me at the email address provided or find us at protochips.com. With that, let's wrap up and get started with the Q&A session. Thanks so much for your time. I hope you all enjoyed this webinar.
Okay, well, thank you very much for your presentations. Apologies. So that brings us to the end of today's presentations and on to our question and answer session. There have been plenty of questions submitted by our participants, and so the first question is, what are some other fields of research that could benefit from atmosphere's capabilities?
Thanks. I'll go ahead and take that question. This is Ben Jacobs. We've got a number of different applications, including semiconductor nanomaterial and growth, corrosion applications, hydrogen storage applications, or anything that you'd like to see in some gas as opposed to in the high vacuum environment of the TEM, because often materials, of course, as we saw in the presentation, have of course, a significant difference in the way that the material behaves in situ as opposed to in high vacuum.
Okay, thanks. And what role do you see environmental closed cell in situ microscopy playing in the future of automotive catalysis research?
That's probably for me. This is George. I would say that there'll be a considerable interest in the future on looking at durability issues, deactivation mechanisms, and so forth. As you saw, the automotive catalyst is a very complicated system, so there's no shortage of different interactions and subsystems there that would be very interesting to understand in much greater detail going forward.
Okay, thanks. And do you feel that there's any risk due to windows breaking, and how often does it occur, if it does occur?
I'll go ahead and take this question. This is Ben again. So as I mentioned in the presentation, we work with the TEM manufacturers, including Joel and FEI, to ensure the safety of the microscope. That's really paramount for the system, to ensure that the expensive components of the microscope, especially the field emission gun primarily, we want to ensure that's protected and that our system, the atmosphere system, doesn't cause any harm to that. So we've built in software features to detect any type of leak. And you have to remember that the gases that flow into the TEM are very, very small. They're very, very slow flow rates. So there's really not a large volume of gas flowing into the TEM. But we've never had an issue with that. We're approved for use in both FEI and Joel microscopes. They've tested our systems, and it's very, very safe to use on the TEMs.
Okay, thanks. And how long does it take to switch gases?
To switch gases, usually we want to decrease the temperature to ensure that it will not react during the gas switching, and then we have to pump in the system and then fill the new gas. Usually it takes 5 to 10 minutes.
Okay, thank you. And we have a question about in situ EDS studies of the nanoparticle. Is it possible to capture live EDS images as the reaction proceeds?
I'll go ahead and take that. This is a new capability. We didn't show it in this presentation, but we have EDS capability now across microscopes. So the new EDS detectors, the large solid angle, like the Super X and the other large detectors from different manufacturers, we're now compatible with all of those. So you can take EDS images at room temperature or at elevated temperature. EDS is pretty important. We recognize the importance of doing analysis inside the TEM with in situ. It's especially important for in situ because, as you saw, the materials tend to evolve and change over time, and if you want to understand what your material is doing, and EDS plays a pretty big role in understanding that. But yeah, we are EDS compatible. Yep.
Okay, excellent. And could you please comment on the stability on the in situ stages when heating or flowing gases during the experiment?
I would like to take this question. Usually, if the temperature are increasing or decreasing, in this case, the gas is going to expanding and result in the bulge of the membrane, and image will be out of focus, and you cannot take images. But as long as the temperature, a certain temperature is reached, it becomes stable, then you can take images, and the stage is very stable. And I didn't see any fluctuation when we have flowing gas. Actually, the flow is very slow.
Okay, thanks. And how do you calibrate the temperature in the chip, and how uniform is the temperature throughout the chip?
I'll go ahead and take this one. This is Ben again. So we use when we calibrate every single thermal device across our products. We have the fusion heating and electrical biasing system in the atmosphere. We use an optical pyrometer, essentially a camera that can measure temperature, and every single chip is calibrated with that particular. It's a commercial camera, and a calibration file comes with that with every chip. And that calibration file is read by the Clarity software. And that's how the software knows how much electrical current to apply to a particular chip to achieve a certain temperature. For the atmosphere system, it's a little bit more complicated in that the gases inside the cell can change the temperature, changes the environment so the temperature can fluctuate, and so we've implemented a closed loop temperature control, and silicon carbide has a particularly nice resistance versus temperature profile. And what that means is as the temperature changes, the resistance of the silicon carbide membrane changes, and we can calibrate for that, and we can measure that, and that's how we adjust the temperature as the temperature changes. Say if you want to remain at 500 degrees and you're flowing in different gases, that temperature can change, and so we're monitoring the resistance again because the resistance is proportional to temperature, and we can actively control that through the closed loop control. With regards to temperature uniformities, I touched on this a little bit in the presentation, but the silicon carbide provides an excellent temperature uniformity across the membrane. So the working area is I believe 99.5% uniform across the viewing area. So it's very uniform, and of course very thermally stable. Okay, thanks. And another question related. Can you comment on the thermal stability of the MEMS system? So, for example, after heating up to 400 degrees Celsius, how long do you need to wait until obtaining high-resolution images in scanning mode? I can start to answer this. Maybe Shu-Yi, if you'd like to comment as well. Drift. This is with regards to thermal drift. As you heat up, of course, the membrane tends to expand, and you get some thermal drift. And with the MEMS style holders and with the silicon carbide technology, we have a very low drift rate. It's because the sample and the membrane itself is very small. So that overall, there's not much drift. But in terms of getting high-resolution images, usually if you change temperatures within a minute or two, you can get pretty good resolution images with STEM mode. Of course, it takes a little bit longer with STEM mode because it's more sensitive to the movement of the sample. And I'd like to, if you'd like to chime in about this, please go ahead.
I think Ben answered pretty much the question, but if they want a number, I think if it's in zone X, and if you found a very good particle, it takes maybe less than 5 minutes.
Okay, thanks. And typically, images in a TEM are collected in TIA or DM. How does image sync work?
Good question. So image sync essentially pulls the signal from any video source and syncs it up with the Clarity software. We can pull in whether it's TIA or digital micrograph or from Joel software or from your EDS computer, what have you. Any source of video we can pull in and sync it up, and you can create custom views. That was just one example of the type of view you can have that I showed in the presentation. But you can have different windows with just the temperature and the pressure, and then the TEM image or the EDS spectrum or what have you, EEL spectrum, and it's very flexible. And then you can take video, essentially spits it out into a video with all of those components. But it works across any source.
Okay, thanks. And can it be done with all types of catalysts?
Yeah, I would say yes. I mean, I think there may be an occasional compatibility problem between the gas cell and a particular material, but I think this is more or less a trial case by case. But in general, I think anything that could be put into a TEM, which means it has to be in the form of a small particle, could be used with a gas cell. Remember that the spacing between the windows is 5 microns, so we need very thin and small pieces of material to do this work.
Okay. And why do you need different types of E-chip for TEM and STM experiments?
I'll go ahead and take this. Generally for STEM, well, let me back up a little bit. For where the reaction occurs on the silicon carbide membrane, that's the heating membrane, because you're heating up your sample and watching the reaction occur. And since it's a closed cell, we have 2 windows, right? As I showed in that diagram in the presentation, there's a top window and a bottom window with respect to the electron beam. When you're in STEM mode, you generally want the sample on top. You want that STEM probe to be as sharp as it can be. You want that to interact with the sample first. So generally, you want the sample on the top window. And that's how Shuyi generally wants, since she's running in STEM mode all the time. However, if you're running in TEM mode, it's just the opposite. You want the sample on the bottom, and that gives you the best resolution in TEM mode. And so, essentially, we've got 2 different options. We've got a silicon carbide membrane that's on the top for STEM mode, and then if you want to do TEM mode, we've got a silicon carbide membrane that can go on the bottom chip. So there's two different options depending on what you want to do, TEM or STEM, and also it has to do with EDS is optimized when the sample is on the top membrane. We get better EDS signal from the top.
Okay. Thanks. And can you continuously acquire images during the reaction? Are there factors that will complicate this, such as carbon contamination?
I would like to take this question. So if there is a very dramatic reaction going on, I think we won't be able to take the images, unless we have an ultra-fast camera, which is usually not the case of STEM mode, maybe TM. And if the camera is fast enough, and you can maybe record all the reaction process. For the carbon contamination, I think this is a very good question, because we do have a lot of carbon contamination at room temperature, and the source may coming from the fabrication process of the E-chips, and they also come from the solvent of the sample. But right now, I think we prefer to work on a temperature about 150 C or 200 C. At this temperature, we will not be bothered by carbon contamination.
Okay, Thanks. And before we got time for, well, we'll go through two more questions, I think, before we wrap up. What's the probe current used for the high resolution ESTM imaging, and what's the corresponding dose rate?
For the probe current, I use it 4 picoampere. And for the electron dose rate, it really depends on your scanning speed and also the magnification of the image. For low magnification, it's usually on the order of several hundred electrons per second per angstrom square. And for very high magnification image, it can go up to like several thousand and maybe even 10,000 as the maximum.
Okay. And finally, if the sample's conducting, can you have SEM and TEM micrographs?
I'll go ahead and take this. So it's an interesting question. So imaging the sample, of course, this is in a dedicated TEM holder. So the holder itself, the chips are at the tip of that holder. And excuse me. However, if you image your sample in the TEM and you'd like to get put that into the SEM to get a different view, maybe a lower resolution view, or kind of a surface topology type of view, then you can put it in the SEM. And the way that you do that is just to disassemble the cell, and you can do a either a pre or post analysis in the SEM before or after you go do your experiments inside the TEM. We've got people who do that type of thing. They take their experiment from the TEM to the SEM, certainly. But as of right now, we do not have a closed cell for the SEM. This is just designed to do closed cell gas experiments inside the TEM.
Okay. Well, thank you very much. I'm afraid that's all the time we do have for questions, although we do have quite a number that are unanswered. Well, thanks everyone for your participation and for submitting the questions that we have. So the questions that we weren't able to answer today will be passed on to the speakers, who will try and contact you later with an answer. So I'd like to take this opportunity to thank George Graham, Shuyi Zhang, and Ben Jacobs for their excellent presentations and for answering the majority of your questions. And I'd also like to thank all of the attendees of today's webinar. I hope you've all enjoyed the presentations as much as I have. So don't forget, there'll be a recording of this webinar that will also be available online very shortly. So that just leaves me with enough time to say thank you all once again, and have a great day.